Welcome to the Getting Started with the Intel Distribution of OpenVINO Toolkit using FPGAs online training. My name is Carl. In this training, we will cover the installation and the environment required to perform deep learning inference using the Intel Distribution of OpenVINO Toolkit with Intel FPGAs. Before we start, let's talk about how the FPGA fits into Intel's portfolio of AI solutions. Intel has the best-in-class hardware portfolio for machine and deep learning, but software is critical to unleashing the full compute potential. To that end, Intel offers an optimized software stack in order to deliver game-changing AI applications. Intel is investing to fully integrate FPGAs into our full stack of software tools, including libraries, frameworks such as Caffe and TensorFlow, and tools like the Intel Distribution of OpenVINO Toolkit. Intel's unified software ecosystem means you can use the same tools across Intel platforms for such hardware such as Xeon, Xeon Phi, VPUs, GPUs, and FPGAs. This enables not just hardware designers, but also software developers to take advantage of the capabilities Intel FPGAs have to offer. To perform deep learning inference with FPGAs, we recommend using the Deep Learning Deployment Toolkit and the Intel FPGA Deep Learning Acceleration Suite, which are both part of the Intel Distribution of OpenVINO Toolkit. So you'll be able to use the same software APIs to perform deep learning inference tasks across many Intel architectures, including FPGAs. The Intel FPGA Deep Learning Acceleration Suite, which is used to accelerate deep learning inference tasks on the FPGA, is part of the Intel Distribution of Open Visual Inference and Neural Network Optimization, or OpenVINO Toolkit. It's a comprehensive toolkit used for developing and deploying computer vision solutions on various Intel platforms. While this training focuses on the deep learning inference on FPGAs, the Intel Distribution of OpenVINO Toolkit also supports OpenCV, implements OpenVX API, and contains the Intel Media SDK. The Deep Learning Deployment Toolkit part of OpenVINO is used to deploy trained deep learning networks through high-level C++ function calls. There are two components to the DLDT: the Model Optimizer, which converts and optimizes trained model on various deep learning frameworks and converts them to an intermediate representation, and the Inference Engine, the second part of the DLDT, which is an execution engine that deploys the network by consuming the IR files through optimized C++ API. Deep Learning Deployment Toolkit can be targeted for many Intel hardware architectures, including FPGAs. When executing on the FPGA, the software part of the DLA suite is invoked, which programs the FPGA with bit streams and is built on top of the Intel FPGA OpenCL platform. Here are more detailed features of the Intel FPGA Deep Learning Acceleration, or DLA suite, which is meant to accelerate inference of convnets. The Intel FPGA DLA suite allows users to take advantage of the FPGA without going through the lengthy traditional FPGA development process. The DLA suite consists of various implementations of the deep learning primitives organized in architectures of FPGA images that are tailored for different types of deep learning topologies, allowing users to implement various networks from AlexNet to GoogleNet and a variety of other topologies without recompiling the FPGA. The DLA architectures implement optimized common deep learning primitives such as convolutions, fully connected layers, rectify linear units or ReLU, local response normalization, max and average pooling, concatenation, and many others. We're constantly adding primitives to DLA as well. When executing DLA library architectures, the data between the layers stays on the FPGA, and for very deep topologies, data just keeps looping through using or bypassing the primitives that are needed for each layer. The diagram shows this particular architecture implementing CNN primitives on the FPGA in a sequence of convolution and/or fully connected, then ReLU, LRN, and pooling layers. In the architecture, the networks are split into subgraphs, which are mapped iteratively to the sequence in FPGA for execution. Some primitives in that sequence are bypassable to support different combinations of subgraphs for the network. Finally, networks that use primitives beyond those implemented on the FPGA can be computed with a hybrid CPU-GPU FPGA solution, all using OpenVINO. The various pre-built images can support many different types of network, including those listed here. Before we talk about the setup to get FPGAs to perform inference quickly, let's examine in a little more detail on the application development process with OpenVINO Toolkit. The first step is always done outside of OpenVINO, training a model. OpenVINO natively support training networks in the Caffe, MXNet, TensorFlow, or ONNX format. If you're using something else like Caffe2 or PyTorch, then those can be easily converted to the ONNX or Open Neural Network Exchange format, which is supported by OpenVINO. With the trained network, it is first processed by the model optimizer, which optimizes your network for inference performance. It will perform operations such as quantization, conversion of primitives, trimming of layers, merging of layers. Their operations are done by model optimizer in a device-agnostic generic fashion. Once the model optimizer is run, it produces an intermediate representation, or IR, which can be consumed by the inference engine part of the OpenVINO. The inference engine is a lightweight API you can use in your application to accelerate inference on many devices. The inference engine can then launch the tasks to the various accelerators. It can even launch graphs in a heterogeneous manner across different devices. The inference engine will load the appropriate plugin for the devices and perform additional device-level optimizations. Lastly, if needed, inference engine supports extensibility to allow custom operations to be performed on the different devices. If you would like to use OpenVINO with FPGAs, currently the boards listed here are supported. The Intel Programmable Acceleration Card, or PAC, with Intel Aria 10GX FPGA, and the Intel Vision Accelerator Design with Intel Aria 10 FPGA. The PAC card is an accelerator card meant for use in data centers. Usage of this board is built on the acceleration stack support, and the board is qualified and validated for several leading OEMs. The Vision Accelerator Design with Intel Aria 10 FPGA is a small form factor PCIe acceleration card meant for low latency video inference for the edge and the cloud. This card adds acceleration capabilities to PCIe host platforms. On an additional note, the Intel Aria 10 development kit is also supported, and the process to support this is actually very similar to the Vision Accelerator Design board, but this will not be discussed in this training. The software and hardware to use the two FPGA boards with OpenVINO are shown here. On the left is what the software and hardware stack will look like for deep learning inference execution on the FPGA-based Programmable Accelerator Card, or PAC, over PCIe in the data center. The Deep Learning Deployment Toolkit can be used over the Intel acceleration stack for Xeon and FPGAs. At the top left, there's the User Deep Learning Inference application. The application is using the OpenVINO Toolkit. The Inference Engine plugin will load the FPGA-specific DLA runtime engine, which is built on top of the OpenCL framework, leveraging the acceleration stack, which is a collection of software and firmware and tools which makes it easy to deploy Intel FPGAs for workload optimization in the data center. The DLA runtime engine interacts with the DLA workload on the FPGA, which contains the various deep learning primitives. The interface on the hardware side is handled by the Intel-generated FPGA Interface Manager, which contains pre-built IP using defined interfaces. On the right is the edge computing solution. Here the software stack is identical to the left, except for at the bottom, instead of the acceleration stack, you have the OpenCL board support package, or BSP driver. On the Vision Acceleration PCIe card with FPGA, the interfaces to the CPU is pre-built as part of the FPGA OpenCL board support package. Again, the hardware is seamlessly hidden from the inference application in the OpenCL layers. As you can see, this suite of tools abstracts away the details of enabling the FPGA and allows software developers to easily leverage the FPGA for inference tasks. With this use model in mind, here are the software requirements. There are really just two pieces of software required for either board. For both, you will need the Intel Distribution of OpenVINO Toolkit with FPGA support. Currently, this is only available for Linux. This distribution includes Intel FPGA runtime for OpenCL, which is needed for the board to communicate with the host, as well as FPGA bit streams and the software layer of the DLA runtime engine. To use OpenVINO with the Vision Acceleration Design FPGA board, you will also need the OpenCL board support package for the Vision Accelerator Design card. This is needed to translate the OpenCL calls to low-level device driver calls for the board. In addition, You'll most likely also need a Quartus programmer in case you need to keep the FPGA image on the flash of the FPGA board compatible with future updated OpenVINO releases. For the programmable acceleration cards, all you need is the Intel acceleration stack for runtime. This includes Quartus Programmer, the runtime environment for OpenCL, and most importantly, the OpenCL board support package. The required FPGA-specific components are described in more detail here. The Intel FPGA OpenCL runtime, which is included as part of Intel Distribution of OpenVINO with FPGA support, is needed because the DLA is built on the Intel FPGA OpenCL infrastructure, so the inference acceleration tasks, such as moving data to the FPGA board and executing different layers, is done through OpenCL calls. The OpenCL board support package is needed for the OpenCL calls to communicate with a given specific FPGA board. The board support package translates OpenCL calls to low-level device driver calls and also allows the programming of FPGA with different bit streams across PCIe. For the PAC boards, this is included as part of the acceleration stack runtime. Lastly, the Quartus programmer is needed to be able to flash or program the board using the JTAG connection with a valid FPGA image to communicate with the CPU when the system boots. The programmer is only needed if OpenVINO version was updated and the hardware in the FPGA is unable to communicate with the newer software without updating to the FPGA image. Again, for the PAC boards, all of these pieces are part of the acceleration stack. The installation of the software required for OpenVINO are listed at a high level on this page. For all boards, first download and install the latest version of the Intel Distribution of OpenVINO Toolkit with FPGA support. Part of the installation process will be to install prerequisite software for things such as Python 3 and other tools. You then verify the installation by running deep learning inference example on the CPU. Then, depending on the board, you'll install different FPGA related software. For Vision Accelerator design, you'll need to download and install the OpenCL board support package. For PAC card, install the acceleration stack for runtime, which includes the OpenCL board support package and other software. Lastly, verify the FPGA board is operating correctly and run the demo on the FPGA board. I will go over these steps in detail in the upcoming slides. For the different boards, I will denote 2A or 2B on the slides if it's only applicable to one of the FPGA boards. Again, first step is to download OpenVINO. To download, follow the link here. You will need to register first. Once registered, follow the download link and be sure to select the Intel Distribution of OpenVINO Toolkit for Linux with FPGA support. Currently, this is the only version of OpenVINO that includes FPGA support. It's ideal to select the latest version of OpenVINO since you're likely to get more stable builds and faster performance with the latest version. Lastly, choose the package, either customizable package where you can select components or the full package. Once OpenVINO is downloaded, install the tool. The easiest way is to execute the install GUI.sh script from the extracted directory. Once the script finishes, you'll need to execute two other scripts to make sure necessary prerequisites are installed. First, run the install cvstk dependencies.sh from the install dependencies directory. This script will install external software such as Python, FFmpeg, etc. that's needed by OpenVINO or the example applications. Then configure the model optimizer by running the install prerequisites.sh. This script will actually configure the model optimizer and install prerequisites for all of the supported frameworks, including Caffe, TensorFlow, AlexNet, Caldi, and Onyx. Instead of running this script, you actually have the option to run individual install prerequisite scripts for each of the frameworks located in the same directory. Once the OpenVINO Toolkit installed and configured, run one of the demo scripts. The demo script will install prerequisites if necessary. Run the setup vars.sh to set up the environment, install neural network models, and run the application example with the CPU plugin. The demo script for classification is the demo squeezenet download convert run.sh. It will run object classification on the squeezenet model. As you can see with the screen capture on the right, you'll need to make sure the demo has completed successfully. After the demo script is run, in this example, the squeezenet neural network model used in the demo will be located in the home directory /OpenVINO models, and sample applications will be located in inference engine samples. Other applications beyond the object classification example include face detection, pedestrian tracker, and many others. Once OpenVINO Toolkit is installed and has been verified to execute correctly on the CPU, it's time to install FPGA-related tools. The software to install depends on the board. We will talk about the Vision Accelerator Design FPGA board first, which is denoted by Step 2A. Later, we'll talk about the PAC board, which will use the designation Step 2B. For the Vision Accelerator Design FPGA board, the first tool to download is Intel Quartus Prime Programmer. This tool is used to flash the board or program the FPGA with the appropriate FPGA image across JTAG connection. When downloading, make sure to use the correct version of Programmer tool. For example, for R3, R4, and R5 versions of OpenVINO, ensure to download Quartus Programmer version 17.1. Another thing of note, because the programmer uses a JTAG connection, you'll need to use a separate USB blaster device to connect to the JTAG port of the Vision Accelerator Design. Once the board is flashed, you don't need either the Quartus programmer or the USB blaster until the next significant OpenVINO update that will require a FPGA connection upgrade. The second thing to install for the Vision Accelerator Design FPGA board is the FPGA support files. You can download this from the Intel Resource Center at the link given. This package is needed to ensure the Vision Accelerator Design FPGA card and the OpenVINO toolkit can work correctly together. Once this software package is downloaded, unpack the TGZ file. If you're using Ubuntu, you have the option to install all the tools environment automatically by executing the setup-env.sh script and the install OpenVINO FPGA dependencies.sh. As of R5, this script is only supported on Ubuntu. If you're using CentOS or other Linux OSs, you'll need to install the contents of the FPGA support files manually. Detailed instructions on that are given on the next slide. To install the Vision Accelerator Design FPGA support files manually, follow these steps. First, copy the 51 USB blaster.rules from the config file to etc udev rules.d directory. This installs the USB blaster driver, so you should be able to see the USB blaster component as a USB device. Next, copy the Perl interpreter executable from the ALCL flash directory to the QProgrammer directory. The Perl is needed to execute the commands that flashes the FPGA board. Lastly, copy the OpenCL board support package for the Vision Accelerator Design board from the config HDLF 1DDRv2 to the board directory where the Intel FPGA OpenCL runtime environment is located. If you use the default OpenVINO installer, this is located in opt Altera. If you're using the Intel Programmable Acceleration Card with Intel Aria 10 FPGA, the only tool you need to install is Intel Acceleration Stack for runtime. You can download the acceleration stack from the link listed on this page. Ensure the version of the acceleration stack you download is compatible with the current version of the OpenVINO toolkit. For example, if you're using the R3, R4, or R5 version of OpenVINO, you will need to get version 1.1 of the acceleration stack. Once downloaded, execute the acceleration stack setup script. This script will install the three FPGA tools, the acceleration stack software, the Intel FPGA OpenCL runtime environment, and the Quartus Prime Programmer in the tool's Intel RTE stack directory. When using the PAC board, there may be some additional hardware preparation you'll need to make. If you're using the acceleration stack version 1.1, you'll need the E10 E40 software package. You may also need to upgrade FPGA Interface Manager or FIM firmware on the PAC board. Follow the instructions in Intel Acceleration Stack Quick Start Guide and ensure that the correct FIM version is loaded that corresponds to the version of the acceleration stack you have. With all of the software installed, it's a good idea to create a script for the OpenVINO environment so that we can easily set the path to the appropriate software and software libraries when using OpenVINO with the FPGA boards. The main purpose of the script is to ensure the FPGA DLA and OpenCL libraries are part of the LD library path and that the relevant FPGA OpenCL tools and utilities along with the OpenCL OpenVINO executables such as Model Optimizer are part of the path. If you're using the Vision Accelerator Design board, use the script to the left. In this script, we first set up the OpenVINO environment by sourcing setup vars.sh. We make sure the inference engine samples are part of the path, and we create an alias for the model optimizer to make sure it uses Python 3. For the FPGA environment, we set the OpenCL context compiler mode Intel FPGA so that we don't automatically load FPGA bit streams when applications are run. We set the Intel FPGA OCL SDK root to the location of the FPGA OpenCL runtime environment. The AOCL board package root points to where the Vision Accelerator Design board support package is located. And we also run the init OpenCL to set up the OpenCL environment. Lastly, we add the programmer directory to the Quartus root dir and make sure the programmer is part of the path. For the pack board, the OpenVINO environment part is exactly the same as for the Vision Accelerator Design board. For the FPGA environment, here we run the init-env from Intel RTE stack. Set the appropriate OpenCL runtime directory as well as board support package, and then execute setup permissions.sh and init OpenCL.sh to set up the correct environment. Once these scripts are run, we now have an environment where we can execute OpenVINO tools and run OpenVINO-based applications. Before the host computer can establish communication with the FPGA board, it's possible you'll need to install the OpenCL driver. For all the FPGA boards, once you have the environment, run the AOCL install command to install the PCIe driver for the FPGA board so the host can communicate with the board. This command only needs to be executed once. Once the driver is installed, you see the FPGA board as part of LSPCI, then you don't need to run this command anymore. With all the FPGA software installed and configured, we'll first verify the board can communicate with the host through OpenCL. First, make sure the FPGA board appears as valid PCIe device by running LSPCI and pipe it to grep for Altera. If you see the Altera processing accelerator, it means the driver was installed correctly. Then run the AOCL diagnose command to ensure diagnostic passed. This command will make sure your board and the OpenCL libraries are installed correctly for OpenCL communication. You can also run AOCL diagnose ACL0, which is the device name to run a detailed diagnose that performs reading and writing of data to the board. Once the board is working correctly, you can run the SqueezeNet demo again, but this time using the FPGA as the accelerator. Before doing that, first choose an appropriate bitstream. For SqueezeNet, it's best to use the SqueezeNet AOCX files. Pre-compiled FPGA bitstreams are included as part of OpenVINO in the bitstreams directory. Here, we're choosing FP11, which is the 11-bit floating point type, and SqueezeNet.AOCX, which is the bitstream optimized for SqueezeNet acceleration. Run the AOCL program ACL0 command with the AOCX file. Then execute the demo script again. This time add the -d hetero :FPGA, CPU. The hetero plugin means we will try to accelerate most layers of the neural network on the FPGA. However, if a particular layer is not supported by the FPGA, for example softmax, then the execution falls back to the CPU. Ensure the demo completes successfully. If it's successful, you are now ready to write your own deep learning inference applications or try another example application. If you would like, you can also run one of the examples manually rather than from a script, or create your own OpenVINO inference engine application. Here are the steps to run SqueezeNet classification example manually. First, create a new directory. Then copy the original cafe files for SqueezeNet into the directory. After that, copy the label files that translate the final categories into text so we can understand. In step 4, we run the model optimizer Python script to convert the cafe model file to the Intel intermediate representation format while doing some optimizations. And finally, in step 5, we can execute the classification example. We can run it with an image on the CPU, run it with the hetero plugin defaulting to the FPGA, or execute it specifying the number of iterations. This concludes the training. As you can see, performing deep learning on FPGAs is easy with Intel Distribution of OpenVINO Toolkit. You just need the OpenVINO Toolkit and the additional FPGA software needed to establish connection to the board. You may also need to configure the FPGA board itself. Once this is set up, you're able to execute OpenVINO applications. For more information on how to write OpenVINO software for FPGAs, please view the Deploying Intel FPGAs for Deep Learning Inference with OpenVINO Toolkit online training linked here. If you would like more detailed information on how deep learning is accelerated on the FPGA using the Intel FPGA DLA suite, please view the Programmer's Introduction to the Intel FPGA Deep Learning Acceleration Suite online training. Here is some additional documentation that may be helpful. OpenVINO related online documentation linked here, which also includes a detailed installation guide for the Intel Distribution of OpenVINO Toolkit for Linux with FPGA support. You will also find additional documentation in the installation directory of OpenVINO. There's one directory for license and installation help, while the deployment tools documentation includes information on model optimizer and inference engine usage. One last thing, when you register for this training, a link was sent to you in your confirmation email that links to a short online survey. Please complete the survey to let us know what you think of this training and how it might be improved. Thank you very much for attending the Getting Started with OpenVINO and FPGA online training. Best of luck with all of your designs.